Good morning, I'm Mr. Meng. This is our 9th grade Earth Science class. They're part of our Frontiers program where we focus on cross-curricular instruction and character development. Today we're going to be looking at the relative scale of objects in our universe. So it should be a very fun lesson. Let's get to it. All right, good morning, y'all. So for our bell ringer, you guys were to come up with an explanation of the size of our sun using anything except standard or metric terms. So no miles, no kilometers. I asked you guys also to vote on whichever one was your favorite. So let's see what we do. Shout out a couple of y'all. Let's see. Ooh. 100 Food Lions, 7 Costco's big. That's great. 500 billion dogs big. That's pretty big. I think the sun is big. Okay, Justin, relating it to some other celestial body. I think the sun is about 400 million whales. Evan, 100 trillion. Ooh, 100 trillion feathers. Who asked if they could put the weight? Was that you, Chris? Let's see. What'd you end up doing? 1 paper clip. Ooh, interesting. How do you weigh the sun? How do we weigh the sun? So today, that's what we're going to be looking at. We are going to be looking at the size and scale of things in our universe, right? So you guys know our sun. You see it every day. It's pretty big, right? It's pretty big. So we're going to jump right into it. As we watch this video, what I want you guys to do, take about 30 seconds to get 1 Post-it note out of your supply bin and a pencil. 30 seconds, 1 Post-it note for everybody at the table out of your supply bin and something to write with. All right, great job, Jason. Yeah, give 1 to everybody if you could. Glenn's getting 1, great job. Emily, there we go. You guys got everybody have something to write with? All right. Let's focus on that during AE. I'll help you out there, Brian. Good job. You won't need your computer for a little bit, Brian, so we'll be all right. Yeah? What's that? Yes, please. Thank you. All right, now, please 45 or close your computers as we watch this video so I know that we have your full attention. Great job. Back table's all ready to go. Back table, great job. Evan's ready to go. Awesome. Now, on that sticky note, what you're going to do is you're going to write 1 wow moment. 1 wow moment. So anything in this video that makes you go, wow. All right? You guys are going to write that down.
Wait, Mr. Meng, are we going to turn this in?
We're going to post it to our big sticky note over there and compare them. Now, as we watch this, please keep volume to a minimum to allow others the space they need to think. All right. All right, so there's Pluto. There's Pluto. There's the moon. There's Mercury. Titan, yes. Titan is a moon of Saturn. Venus. There we have Earth.
Wow.
Ooh, okay. So now we're getting into exoplanets. There's Neptune, one of our gas giants. Uranus. Saturn with its rings. And Jupiter. All right, so there's our sun, right? Our sun's pretty big, right? Where's Earth in this? Jason, where's Earth?
All the way down there.
All the way down there, right? Little bitty, you can barely even see it, right? So our sun is pretty big, right?
Wow.
So that's the black hole at the center of the Milky Way.
How do we know if there's a black hole in the middle?
Ooh. So our sun is pretty big, right?
Look at these. Yo, what's that? That's pretty big.
Are these stars?
So, great question, Emily. These are stars. These are stars in our known solar system and universe. Now, this is a blue hypergiant. I asked Jason where our Earth was last time. I want you guys to try to find our sun down here. It was before that little blue dot right there. All right? So, but our sun is pretty big.
Wait, Mr. Meng.
Welcome back, Tom. Hang that up. Whoa. Now those are two black holes that we know about. And now we're zooming way out. Way out. That is a nebula. That is where stars are born. Remember to write down one wow moment from this video. Ooh, Eagle Nebula. Huh. How are the measurements or distances changing here? Yes, a smaller galaxy. So that's only 220 light years across.
This is bigger than the biggest star.
Ooh. Sleeping Beauty. Okay, another galaxy we know about. And there is our galaxy, the Milky Way, over 100,000 light years. Now that's pretty big, yeah. Whoop. Wow.
We're actually small, never mind. Along to me, so how it is.
Good try. And there is our observable universe. So we went from hundreds of kilometers, which we can literally measure here in Virginia, all the way out to 93 billion light years. Now, I want you to think. Think, don't shout it out. Is a light year distance or is a light year time? Think about it. Don't shout it out. 10 seconds, turn and tell your neighbor. Go. Evan, what do you think it is? Is a light year distance or time? Time. Okay. What is it? Time? Okay. All right, let's come back together up front. I want you to raise your hand if you said time. Okay. I want you to raise your hand if you said distance. All right, those of you who say distance, why do you say distance? Jason. What an amazing observation. Look at that. So, remember, it's divided by something? Okay. It is, and we can't quite see that. What is that? Ooh. What? Whoa. Huh. So, those of you who say time, why do you say time? Joseph. It takes time for light to reach us. It does. It absolutely does. Year. Okay, you heard the word year. Great reasoning.
I feel like it's like both because like a light year might be like how long light takes for its year to pass around.
Ooh, good point. Do you guys know how many times light can go around the Earth in 1 second? It is 7. It's 7.2 times. So in 1 second, light travels around the Earth 7.2 times. Now, 1 light year, which I know we've mentioned it, but 1 light year equals the distance light can travel in 1 year. So it is distance. All right, let me put it to you this way. When you guys walk down the hallway to another class, right? You guys go about the same speed every day, right? You walk. If I said, how far can you walk in 1 minute? That's a distance, right? So that's the same thing as a light year. How far can light travel in 1 year? Ooh. So it's about, give or take, it's about 300,000 kilometers per second. That's how fast light is moving. Like 1 second goes around the Earth 7.5 times. All right? Cool. Now, what I want you guys to do is carefully take those Post-it notes. Actually, let's share some of those. Who wants to share their wow moment? What made you guys say wow in that video there? Jason?
The Eagle Nebula.
Ooh, the Eagle Nebula. Why'd you like that? Why'd that make you say wow?
Because it was like, it looks like an eagle, and it's like the space and the galaxy can make like art. It's like, it's interesting.
Ooh. Let's try to find that. Very cool. Where was that? That one was our nebula. That was the Tarantula Nebula. There it is. So yeah, these nebulas are often named after kind of what they look like. And we'll get there. So there was another one here that was like the Tarantula Nebula. Has anybody ever seen a tarantula? It's kind of those colors, isn't it? Kind of like brown and, yeah, kind of cool. Emily?
The galaxy on the left, the smallest one, even though it's kind of like small, it still has lots of light.
Even, great observation, yeah. Even the smallest galaxy that was 220 light years across, right? It still looked like our Milky Way spiral galaxy. It still had a ton of light in it. So this is just, I mean, going back here, if we zoom all the way back down to where these stars start, and we zoom back into our sun, all the way back here, beyond that black hole. Wild. Really wild. All right, now, one other question I have for you. Why are these stars different colors? Ooh. What made you say that, Chris? You talking about the Doppler effect?
Yeah.
And redshift and blue shift? Excellent thought there. Excellent thought. So, that specifically deals with galaxies and their movement, right? Good deal. What do you think, Antonio?
Maybe they're made out of different like materials.
Ooh, different materials. Do you guys, does anybody have a propane stove at home? Propane stove. You turn a gas stove? Gas stove? Vale? Yeah, with the knob? And the fire? Okay, so you turn that flame on. Hold on. You turn that flame on. What color is that flame? Blue. But when you guys go to a campfire, what color is the fire? It's red, right? Huh. Interesting. Interesting. You guys have a lot to say today. Yeah, Jason.
I think that it's like the
The intensity of the heat. Great.
If you crank the stove on to like low, it's gonna be red. But if you crank it up to high,
Okay.
more and more like gas is released, it turns like blue. And I think that's the thing that goes for stars. Is that the hotter it is, the different color it changes.
The hotter it is, the different color it changes. Excellent. Don, what do you have to add? So yeah, it's you guys are all hitting it right on the head. So yes, stars, remember, they create fusion. They combine elements from hydrogen into helium to heavier elements like oxygen and iron. Now, when they start burning hotter, just like your propane stove burns hotter than a campfire, that blue, well, I won't tell you yet. Let's get into our next activity and find out. Now, what we're going to do, you guys are going to receive about 4 to 5 stars. So right now, we are on our HR diagram class activity here. You guys are going to receive 4 to 5 colored circles representing known stars in our solar system and universe. Your job is to accurately plot these stars that you get on our graph up there based on the temperature and luminosity. So when you get your stars, the first thing you should do is identify their temperature and their luminosity. Now, if you need a refresher on how to plot those data points on a graph, it is on that anchor chart right there. I will do an example for you using our sun that is already on the board. Now, the sun, it has a brightness of 1. Ooh, so that is, what's another word for brightness?
Intensity. Luminosity.
Luminosity, that's right. That's how we measure how bright a star is. And if you guys noticed, it says suns beside your brightness, right? So our sun, the brightness of our sun, can you guys look at the sun with your eyes? Right, it hurts, right? It's very bright. Chris? When you look at the sun with your eyes, it's very bright, right? That is our standard brightness. Anything with a decimal is going to be less bright than our sun. Anything higher than 1 is going to be brighter than our sun, right? Now, as far as temperature goes, temperature is on which axis here?
The x-axis.
Absolutely, our x-axis. Notice this isn't like a standard graph where we have 0 and 0 over here, though. Notice how temperature is increasing from right to left. So, if I have my sun here, our sun, our wonderful star, it has a brightness of 1. That is our standard measurement for brightness. And it has a temperature of 4,800 degrees Kelvin. You guys, we don't need to get into Kelvin right now. It is kind of like Celsius, kind of like Fahrenheit. It's just a measure of energy. Now, along our x-axis, where is 4,800? Over here?
Yeah,
Around there?
40.
Brandon, you're shaking your head. Why?
Should be close to 4 or 5,000.
Ooh, cool. So we saw 4 and we jumped to it. Make sure you guys are looking at where you are. All right? So it is increasing from here to here. So we go 4,800 just below 500. And remember, if you guys need help on how to plot this, review that anchor chart. We're going to go straight up from our x value, and we're going to find our y value. We have a luminosity of what for our sun?
1.
Who said that? Remind me later. You get 1 over here. We go straight over, and wherever those two intersect, that's where you're going to plot your star. So Isaiah, 4,800 up, 1 over. So what you guys should be doing right now is looking at where your brightness is and where your temperature is for each one of your stars, right? Now, once you guys are ready to plot your stars and you are confident that you know where each one of your stars are going to go, you can go up to the board and begin plotting them. Good job.
You only put one of them, he said? Yes, it does.
You have two sons. That's one son. Y'all right beside each other.
Here we go. Do we see a pattern emerging?
That the reds are on that side and then the dark blues are on this side.
Huh.
Yeah, I was right.
Oh, you guys are being meticulous about this. Now, I want you to make an observation about the board here. I want you to make one observation. Think about it. You're not going to tell me. You're going to tell your neighbor. All right? 10 more seconds. Make one observation. Turn and tell your neighbor. Go.
There's giant, there's small planets, there's white planets.
What observation is that?
This is like the orange and yellow.
Mm-hmm. No, they're
This
not.
is the blue.
But why the white planets all the way down there?
Because he said we're not doing these ones.
They're not,
That's
they're
why
not on
we
the
took
board
it off
yet.
the board.
Yeah, decrease your fast. Because I'd be. Do you think you're fast?
Now, Chris, what's your inference?
I thought I had one, but I forgot.
I bet you do. I'll come back to you. Don, what do you think?
It makes a gradient.
Nice. What was that word you said? Gradient. What is a gradient?
It's like when the colors change the gradient.
Ooh, when the colors change, kind of like a sunset, right? You ever seen that? It's really cool. So now, looking at our x-axis, I got a question for you. Does temperature influence the color of the stars? Thank you guys so much for joining our lesson today. I hope you guys enjoyed it, and we look forward to seeing you next time.
Go Tigers!